Okay, so if you go to your computer, to your Canvas, this is what this semester's medical forensics will look like. It's a crime scene, do not cross, with the blood splatter. And if you click on that and come into it, you'll see Chapter 9, Forensic Serology. Click on Daily Schedule. Under Daily Schedule here, I've got the PowerPoint in PDF form, so you can follow along with me. You've got notes in Word document form, so if you want to type in your notes, you can. And you've got notes in PDF, so if you've got, like if you grab the iPads, you can actually write in your notes and then save them digitally if you'd like to. So this is what we did last time. We talked about the beginning of bloods. Notes go here, and then your assignment is from the book, and it goes here. Okay? So on the assignment from the book, on your ping page, and remember on your front here, you have an extra credit assignment at the very front if you want to take the vocabulary and define the vocabulary. I haven't got a place yet to upload it, but I will. You can upload that and get some extra credit there. And then the standards that we're covering from the state are on the front. On the second page, just to review real quickly, are your bookwork assignments. And then your class notes. I've written the pages of the packet that need to be turned in for each of the class notes. And then the labs that we're going to do for this unit. And we are going to, I think, do the blood typing one next time. Okay. So is everybody okay where we're at right now? So we should have being turned in notes 1 and assignment 9.1. If you haven't got to them, it's okay. We'll have some time next time. The Tuesday stuff, I'm going to actually copy it down to the next one, so you'll have another day. We'll do some notes, but you won't be assigned to have it turned in until the end of that time. But again, everything is due by, I think it's the 17th of March. It'll have a due date on there. That due date is the test or ending of this unit before we go on to the next unit. So try and keep you going like you should, okay? All right, so having said that, let's go to the blood types. There are 4 major blood types. How many know what their blood type is? What's yours? A? Okay, positive or negative, do you know? One of the two. Okay. Positive. I wish we could still do blood typing here. We can't because we can't do blood, but because it's pathogenic. But we're going to do a lab that will simulate that. Okay? When you have a parent, and each parent has what we call 2 alleles. They can give you 1 of 2 of their alleles. So here Dad has a blue and a green, just visually so you can see, and Mom has a purple and a green. So you could end up with a blue-green, a blue-purple, a purple-green, or green-green as far as the alleles of a kid. You inherit 1 from your mother and 1 from your father. Now, how does this affect forensic science? It's all about the paternity. So if a person comes in, a mother comes in with the baby and says, he's the father, and the guy says, no, I am not, and we know what their blood types are, we can say, and know what the child's blood type is, we can see if that's even a possibility before we go to the expense of doing a DNA testing. So these genes are determined from proteins called agglutins. They exist on the surface of everyone's red blood cells. Red blood cells have structures that we call antigens. Okay, the antigens are on the blood cell, the red blood cell. They're grouped into classification systems that we already know: A, B, and O. Okay? So we're going to go into this a little bit more. So antigens, they're grouped into systems determined by the relationship to one another, known as blood type. Okay, we okay to go forward? Okay. All So if we look at each of the blood types, A can be an A positive or A negative. B can be a B positive or B negative. AB can be a positive or negative. And O can be a positive or negative. Now what does that mean? Well, in A, that means A has these antigens that are attached to the red blood cell that attach to or identify as A. So when A bumps into A, they're like, oh yeah, okay? So they also have within A antibodies against B. So antibodies against B. So if I happen to mix A and B blood, it will curdle. It will cause clumping. So that's why it's really important when we go to the hospital that they know your blood type before they give you blood. Because if they give you the wrong blood, it could cause blood clots within your body. Okay? So B has specific antigens, and it has antibodies against A. AB has both the A and B antigens, but has no antibodies against either A or B. O does not have any antigens, but it has antibodies against both A and B. Okay? And I know down at the bottom it says blood donors. We're actually going to cover that next time, so that's why I'm going to hold off having you turn that in. So did you get the fill-in points for A, B, and O on that chart? Okay. So go ahead and flip to the next page. We're actually going to do the bottom one first. So I'm going to talk about it a little bit, and then we're going to do the bottom one. Okay, there are how many? 6 possible combinations of genotypes and 4 possible expressions of phenotypes. Oops, let me go back. So genotypes would be like AA and AO. Those are genotypes. But the phenotype, what's expressed on both of these is A. Okay? So we need to know what a genotype is versus a phenotype. There are 3 different alleles, A, B, and O. We already talked about that. Remember that an AA or an AO is still going to read as A. A BB or BO is still going to read as B. AB is AB, and O is just O. O is sort of like the recessive gene. It doesn't show unless both of them are there. So here we have this chart down the bottom. So here comes in this mother with the baby, and she says, he's the father. Well, if she has A, and he has AB, and the child is O. Okay, so then we go through, and we're trying to figure this out. This is a chart that they keep pretty up to date, so they can just look at it, so they don't have to figure it out every time. So if we look at this, A is really AA or AO. So that means the mother could give an A or an O. So these are the possibilities. Dad could give an A or an O. If the dad was a B, he could give a B or an O. Mom still could give an A or an O. So all the possible choices. If mom was an A, dad was an AB, we get all these possible choices. If mom was an A and dad was an O, here we've got an AO. Well, I said mom was an A, dad was an AB, the child was an O. Is it possible that the dad is that child's father? No, because he can only give an A or B, which is going to override any O. So right away we can say, I'm sorry, that's not the father. You must have somebody else that father. Okay, so going through the second row is going to be the same kind of thing. B could be B or O, AA or O, so we get 4 choices. Goes down to 3 choices when we have the same thing. Notice, same thing for A, we get 3 choices. On B and AB, we get 4 choices, so if they're totally different, we end up with 4 choices. But anytime we hit O with something else, it's 2 choices, it's down to 2. Go with AB all the way across. You'll notice it has 4 choices, 4 choices. When it's A and B, it goes down to 3. When it's A and O, it goes down to 2. Now, what if we have the O as a mother? I only have 2 choices, 2 choices, 2 choices, then 1. If both parents are O, the kids can only be O. Okay, so knowing that, what could the father of the OO have been? So we're looking for children that have OO blood. what could he have been? If the mom was an AO, what child would end up as an O? That's okay.
Ask the question one more time.
Okay, if the mom was an A and the dad was suppose the dad was an AB and the child was an O, we determined that the child couldn't be AB's dad. Couldn't have AB as a dad. What could she have had or he have had as a dad? So A, B, or O, right? Because there's an OO in each of those.
This is not.
Okay, so if mom was an A,
Yes.
and the supposed dad was an AB, and the kid was an O, there's not a choice here that's an OO. So this dad cannot have a kid that's an OO. It's not a possibility. So then I asked, well, who could have been? What blood type could have been the child's?
A, B, or O.
Yeah, A, B, or O, because all of them have an OO. And the only time you're going to get an O is an OO, because they both are recessive. So if it's with anything else, it's going to show as an A or a B.
Well, that's a lot.
Okay, so that would narrow it down. Now, this is what? This is the genotype. What do we usually see when we go to the hospital? Do they test for the genotype? No. They test for the phenotype. So here, we will see A and O. Here we'll see all 4 possibilities. Here we'll see 3. Here we'll see 2. 4, 2, 3, 2. 3, 3, 3, 2. 2, 2, 2, 1. Okay? So if you want to use a different color to show the phenotype, the black is the genotype, the red is the phenotype. That's what we would see. Whoa, and I enlarged that, didn't I? Sorry. Got real excited and pressed the button twice. It enlarged. Okay, when you get that written down, I want you to see if you can just fold this and see if you can make this one right here, if you can figure out what they should have been without seeing your results on the bottom. So either fold it off the side so you don't see it, but see if you can figure out if the father was A and the mother was A, what are my possibilities? If the father was, so I've moved the places. I put the father on the left and the mother on the top, but it's basically the same. I want you to see if you can figure out what they could have been by yourself.
So the red is what it does when it's like blind.
The red is what I'm going to see when I test for the blood type.
Okay.
And that's called a phenotype. The black is a genotype. That's like actual genetics.
Accidentally did it backwards, but it works.
Yeah, just go ahead and put this one down because we're going to be referring to this. And this one doesn't have the AB.
This one will be.
The top one doesn't.
Still,
The others should be okay, but this,
what is still
so when it's an AB, the dad can either give an A or B, not an O. Does that make sense? So there's one more column right here. One more column here or down here. So just really quickly do that one real fast. I'll leave it up for a minute so you can see it. If you're having problems,
I'm confused. So what are we supposed to be doing? Like,
so here, dad can be an A or it could be an
yes.
It's very A or A. The possibilities are same thing like this. So here, combine this. It could be an AA, it could be father, and then it would show if it will be testing A or not.
So you're trying to figure out.
Yeah, I want you to try and do it by yourself without me interfering.
Okay, so we just pretty much copy this.
Yeah, I don't want you to copy it. I want you to put the phone or something over it and see how to do it yourself. Okay, does that make sense?
That's
Yes.
Okay, so. So he's only
Yeah.
this mom got you ready. So she can be an A. Yeah, she can be an A or no. So here, it's A and A can go together. So it's copy.
I understand that.
That's my genotype. My phenotype would be A. Mine is just those.
So everyone of us has a copy.
Just want you to be
I
able
have
to.
this
Well, it's just a grass.
I remember Brad you talking about it, but I was so out of it.
So basically, if you can get this, you can solve most of it.
like
I feel like we got this.
it's the dream team right here.
There's too much.
So when it's with only A's,
Oh,
Is anyone having problems or need extra help? I'm willing to help you. Are you guys getting this?
I wish Chloe was here.
Oh.
So basically,
Mother is oh gosh, no, it can't. Yeah. Yeah. Oh my god. This is like B.
so that's a genotype. Phenotype.
I feel accomplished.
Are we feeling like we're getting this?
Yes.
Does anybody need help?
BB.
I think I got it.
Little people, because like I feel like in my head I see like little A's like with that little B like A's.
No, she didn't. She helped me.
Okay. So hopefully you've got the main idea here. So this one is flipped, but you can basically be the same kind of thing. It doesn't matter if it's the mother's blood or the father's blood, right? An A to an A will give me an A or an O, which is either an A, an AO, or an OO. Those are the choices for my genotypes. My phenotypes are A and O. So here I've got the phenotype showing. What kind of blood type would be showing? Okay, just remember that A and A make an A, A and O make an A. BB makes a B, and BO makes a B. That's a big
So O is always not shown unless it's full.
right. Always recessive, so the only time I see it is when I have two O's. Okay, now we're going to go forward here, maybe. It thinks my finger is now a pen. And we're going to watch a little thing about the man with the golden blood. So on the next page, I'm going to answer some questions before we get started so that we can, when we get out of here, guys keep me track of me, 11:03, so we don't have a lot of time. So I'm going to tell you a lot of things really quickly, then we can listen to it. So the role of red blood cells in the body is to take oxygen to the body and bring CO2 back to the lungs to get rid of it. That's what red blood cells do. So write it down in your own words. We're now on this page right here. And I'm walking you through the questions. And then we're going to watch it. So red blood cells take oxygen to the body and CO2 to the lungs to get rid of it. That's the first question there, case study. The top. Okay, the next one.
CO2,
CO2 to the lungs to get rid of it. That's what red blood cells do.
oxygen 2.
Oxygen to the body, CO2 from the body to the lungs to get rid of it. Okay, number 2. Describe the difference between an antigen and an antibody. An antigen is what's on the red blood cells. Remember, you can shortcut it by RBC. Red blood cell has an antigen on the surface. And antibodies in the plasma. Antibodies in the plasma, and it attacks foreign bodies.
Okay, so red
Antigen is on the red blood cell. and it identifies what type of blood it is. Antibodies in the plasma, and it attacks foreign matter. So what we're going to do to identify this is we're just going to get a well plate, and the well plate has wells this way and this way. And what we'll do is we'll take our sample of blood, whatever it is, and we put it across 4 wells. The first well we're going to test and see if it's A. We'll put anti-A in there, and if it coagulates, we know it's A. In the next column over, we'll put anti-B in there. If it coagulates, it's B. In the next one over, we'll do the RH factor, the positive or negative. It's called anti-D. If it coagulates, it's positive. If it doesn't, it's negative. And the fourth one should just be regular blood. Okay, so we can look and see what type of blood it is. So how are blood types determined? By how they coagulate, or you could call it curdle, in the presence of other antigens. So that's number 3. So it depends on how they curdle or coagulate, or I don't know.
How do you spell antigen?
It's right above a anti.
Is curdle with a D or a T?
I am a
D.
horrible spelling, so do your best.
D, like curdle.
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 Okay, and then what determines if a blood is positive or negative? This is the RH factor. The RH factor is anti-D. So if anti-D is curdled, it's positive. If it's not, it's negative. And Thomas, will learn here in the report, if we can get to it real fast, is one that has one of the first ones that we found that had RH null blood. It's either positive or negative, the RH null blood. And so what year was that? It was 1967 is when it was reported, 1967.
That's 3 years before Barbara Streisand.
Number 6, how many people in the world carry RH null blood? 50. No, 40. It's 40. Now what makes this type of blood very significant is it is actually like a mediator between the RH negative and the RH positive blood. And we'll learn why that's important in a minute. So just call it like a mediator between negative and positive RH blood.
Who was Thomas?
So Thomas was the first one that was identified as having RH null blood.
So he had it?
Mm-hmm. And then on number 7, summarized golden blood that was used for Father Aniki's 70-year-old grandmother. Basically, she needed heart surgery, but she has a very, very rare type of blood. And so they had to go to several different countries. They tried to figure out where she could go to get the blood, but the problem was getting the blood across country lines. There was a lot of bureaucracy. So they actually had to fly the blood donors in to where she was having surgery in order to have the blood donated there to have surgery, because her blood type was so rare. Okay, and IB Girl stands for International Blood Group. Let me see if I can find it real fast. I can't remember all the names. Here it is, International Blood Group Reference Laboratory. And it's really important because it keeps track of all these rare blood types and the people that have them and where they are in the world. The temperature that blood needs to be kept at is 4 degrees. If it goes too high or below 4 degrees, then the red blood cell will not transfuse. So number 9 was 4. And then how many in the world have O negative, Lutheran B negative blood? 550. So, and what makes this type of blood significant is it is a universal donor to all. And then James, who we're going to be listening to about here, how is he connected to the RH null blood? He is the only one in Australia that donates RH null blood and has saved over 2 million babies because of it. And then people with this blood type often lead difficult lives because they're asked to come and donate to be somebody's savior, but the people asking them to donate cannot pay them. So they have to get them to, they have to pay their own way to parts of the world and pay to donate and pay to do everything. Okay, so having that said, I'm going to actually start this little video and we'll see how far we get with it.
Type AB positive. They're going to be the universal for plasma. That's the liquid part of our blood that carries cells and nutrients through our bodies. It's most often used in emergencies for patients requiring massive transfusions. And there are also forms of rare blood. That's the case in Australia, where the man with the golden arm has spent a lifetime of giving to save newborn babies from a blood disease. On the surface, James Harrison is just an average guy. He loves his daughter and grandchildren. He collects stamps, goes for walks near his home on Australia's central coast. But it's what's under the surface that makes James extraordinary.
I got nicknamed the man with the golden arm.
Specifically, it's what's flowing in his veins. James's golden arm, his right arm to be exact, from which he's donated blood nearly every week for the past 60 years.
Well, in 1951, I had a chest operation, which they removed the lung, and so I was 14. So when I came out of the operation, or a couple of days after, my father was explaining what had happened because it was 11 hours on the table in those days, and he said that I'd had 13 units of blood and my life had been saved by unknown people. He was a donor himself. And so I said, well, when I'm old enough, I'll become a blood donor.
At that time, you had to be 18 to donate blood in Australia. Not long after James became a donor, doctors called him with an idea. His blood, they said, could be the answer to a baffling problem in Australia.
In Australia, up until about 1967, there are literally thousands of babies dying each year, and doctors didn't know why. And it was awful. There were women who were having numerous miscarriages and babies were being born with brain damage. Researchers discovered anti-D, and then James was discovered to have this antibody in his blood, which was amazing.
It's called rhesus disease, a condition where a pregnant woman's blood actually starts attacking her unborn baby's blood cells. In the worst case, it can result in brain damage or death for the babies.
Australia was one of the first countries to discover a blood donor with this antibody. So it was quite revolutionary at the time. James has effectively helped babies in Australia, but he's helped, babies all around the world.
James worked with doctors to develop a vaccine using the antibodies in his blood. A vaccine his own daughter even ended up needing.
That resulted in my second grandson being born hale and healthy, and it makes you feel good yourself and that you've saved a life there, and you saved many more, and that's great. Well, today I'll be making my 1,101 donation.
As he's done more than 1,000 times before, James gets in his car and heads to donate his plasma. He's a familiar face around here, and no matter how many times he's given blood, there's one thing that will never change.
Never once have I watched the needle go into my arm. I can't stand the sight of blood, and I can't stand pain, so...
At the donor center, James's plasma is separated from the red blood cells. He gets those back. And the plasma heads off to become the vaccine.
He comes in every week or two. He donates his plasma. His body remakes the antibodies very quickly, and he's able to donate again. So it's really very easy for him to do, and he certainly doesn't see it as anything big. And that's the other rare thing about James. He thinks his donations are the same as anybody else's. He doesn't think he's remarkable.
His blood is precious. In his home country, James is considered a national hero, but he doesn't see it that way.
It becomes quite humbling when they say, oh, you've done this or you've done that, or you're a hero. No, I said, it's something I can do. It's one of my talents, probably my only talent, is that I can be a blood donor.
But it is a big deal. James and his vaccine are credited with saving the lives of more than 2 million babies. That's according to the Australian Red Cross Blood Service. Yes, 2 million lives saved by one man's blood.
every batch of anti-D that has ever been made in Australia has come from James's blood, and more than 17% of women in Australia are at risk. So James has helped save a lot of lives.
So this is Samuel and he's 5 weeks old.
One of those lives is baby Samuel. He's just 5 weeks old, and his mother is here to meet James for the first time.
Hi.
Hello.
Good, how are you? Well, nice to see you.
Hello.
This is Samuel.
Hello, Samuel.
Christy Pastor first got the vaccine injected during her second pregnancy. With James's antibodies in her blood, little Samuel is her 4th happy and healthy baby.
They just said you needed the vaccine. I didn't think about it any further. And then looking into it a bit more, obviously I found out about James and how amazing he is and how many donations he's made, and that it was all because of him.
Doctors still aren't exactly sure why James has this rare blood type, but they think it might be from the transfusions he received when he was 14 years old after his lung surgery. He's one of no more than 50 people in Australia known to have the antibodies. That's according to the Australian Red Cross Blood Service.
Yeah, I think James is irreplaceable for us. I think we can't really underestimate what he's done, and I don't think anyone will be able to do what he's done. But certainly we do need people to step into his shoes, and he will have to retire in the next couple of years. And I guess for us the hope is that there will be people who will donate that will also have this antibody and become lifesavers in the same way that he has.
James is 78 years old. In Australia, you can donate blood until the age of 81. So as long as he can over the next couple of years, you can bank on James showing up here without missing a beat. Another meeting, a world away. As Stuart prepares to make the journey from England to America.
Go get your stick.
2 years ago, he
This is
donated
just the
stem
next one
cells to
coming up,
Celia,
so we're gonna
a complete
stop.
stranger in the United States. And they are about to meet for the very first time.
Okay. So, just really quickly, if you'll, like I said, start saving a $20 bill. We'll probably do it next week. I'm hoping that test kits will come in and we'll test their bill next week. And then we're going to test the